Swayam Prabha. Digital India. Educated India.
Welcome to lecture number 2 for flow of water through soils. In the previous lecture, we have understood about the concept of flow of water through soils, and we discussed about Darcy's law, which relates discharge velocity and coefficient of permeability and the hydraulic gradient, a parameter which is defined as I is equal to H by L. H is the head loss which is taking place between say 2 points A and B separated by a length L. So, in this lecture we will be seeing when water flows through soil, how these effective stresses change, whether they remain constant or increase or decrease. So, in the review in the previous class, we have understood about fluid flow through soils, and we introduced the Darcy's law after Darcy 1856, and introduced a very important parameter in soil mechanics called coefficient of permeability. And we have tried to deduce relationship between seepage velocity and discharge velocity, which we also named as superficial velocity. So, now in this lecture we will concentrate on flow of water. When flow of water takes place through a porous media, then what are the changes in geostatic stresses with flow of water through soils. So, let us concentrate this particular effect in the case when water flows through soil. So, before discussing that, in this slide, as we have seen in the previous lecture, the soil is assemblage of particles. In this particular slide, the granular particles are shown like solid grains, which are possible in coarse grained soils. But in case of clay soils, depending upon the structure, it can have a flocculent structure or a dispersed structure or semi flocculent or dispersed structure. So, depending upon that, the float shall take place across the plates, that is the particles are perpendicular to their plane. So, here the soils are assemblages of solid particles with interconnected voids through which the water can flow from a point of higher energy to a point of low energy. That means that for the flow to take place, we said that there should be a higher energy should be there at point, and a lower energy should exist at another point. So, then the flow can take place from a point of higher energy to a lower energy. So, this concept we have already seen, but let us look once again very important concept which we should remember in flow of water through soils. Here total head is H1 and the reference datum which is shown here, and the elevation head is Z1 and pressure head is P1 by gamma W. So, total head is equal to H1 is equal to P1 by gamma W plus Z1 at point 1. At point 2, total head is H2, that is summation of P2 by gamma W plus Z2. So, if you observe that when H1 is greater than H2, not necessary that down the hill the flow can take place from 1 to 2 in the confined aquifer conditions like the one which exists in below the ground level. So, for the flow to take place, the energy which is spent by the water in flowing through the soil is the H1 minus H2, that is delta H, over a distance which takes place, say L is the length between 2 points. So, then hydraulic gradient is said to be here as H1 minus H2 divided by L. Now, while introducing when the concept of flow of water through soils, we said that and we assumed that the soil is assumed to be completely saturated and frictionless, assuming that frictionless boundaries are there, and we also assumed that the flow is in the laminar regime. That means that for soils, when the flow takes place through soils, the Reynolds number will be less than 1. So, we discussed that except for some coarse sands and gravelly soils, the Reynolds number will be very much less than 1. That means that the flow will honor the laminar regime. That means that it will be under the laminar regime. Then we define here Reynolds number is equal to rho v d10 by mu, where d10 is the effective particle size, v is the discharge velocity or superficial velocity, or which that is the velocity through which the water is flowing through a particular area of cross section. And we also discussed that the flow cannot take place through particularly passing through the contact points. So, it can actually take a winding path, and we described that path as a tortuous path. We idealized that at a macroscopic level as a path which is indicated called as a flow line. Okay. Now, when you look into this flow of water through soils, and we introduced the concepts like permeability, one parameter which indicates that ease with which the water flow through soil. So, permeability is part of the proportionality constant in Darcy's law. As you all know, the Darcy's law is equal to V is equal to K I, and V is proportional to I. So, as long as the flow is in laminar regime, it satisfies this particular Darcy's law. Once, except in gravelly soils, rest of the other soils, this particularly Darcy's law remains valid. Darcy's law remains valid. So, which Darcy's law, which basically relates the discharge, that is the flow rate, and fluid physical properties like viscosity, the viscosity of the permeant under consideration, to a pressure gradient applied to the porous media. That means that at what head it is the flow is taking place, that is the head loss or a pressure gradient. So, the proportionality constant specifically for the flow of water through a porous media is hydraulic gradient, hydraulic conductivity. The proportionality constant specifically for the flow of water through a porous media is hydraulic conductivity. So, permeability is a portion of this and is the property of the porous media only, not the fluid. In naturally occurring soils, this particular permeability can range from different magnitudes. That means that for fine grained soils, it can have a particular value, very low value, and for a coarse grained soils, it can have very high value. So, this value of the permeability depends upon the type of the soil, and it depends upon the many other factors like its gradation, its denseness, and its structure. So, which we are going to discuss in forthcoming lectures. So, in naturally occurring materials, this permeability ranges over many orders of magnitude. For a clayey soil and sandy soil, more than a million times of magnitude difference will exist. So, that indicates that how difference is the behavior when we consider a clayey soil and a sandy soil. So, let us consider like we did in the previous class, in the flow direction, consider 2 points A and B, which are separated with a head loss by distance L, separated with a distance L between AB, and total head at A is say HA, total head at B is say HB. So, the difference in head between A and B is HA minus HB, that is delta H. So, the hydraulic gradient can be set as HA minus HB by L, where L is the distance between 2 points A and B where the flow is taking place. So, as a particle of water proceeds from A towards B, it exerts a frictional drag on soil particles. So, when the flow is taking place from A to B, it exerts some frictional drag onto the soil particles. So, while inducing the frictional drag, whatever the energy it has to flow through the soil, it will try to dissipate. So, in the process what will happen is that the water which is actually flowing with a certain energy will be losing the energy as the water is flowing through the soil. Once it comes to the exit point, the complete energy loss will occur. That indicates that the complete dissipation of the energy which was there at the entry point is said to be dissipated. So, in turn produces a seepage pressure in the soil structure. That means that this frictional drag, when it is taking place, produce a seepage pressure which can induce changes in the effective stress. For example, it depends upon the direction of the flow. If it is say downward, then it can push the particles into the denser packing positions. If it is an upward position, so there is a upward direction, then the seepage pressure acts in the direction of the flow and can agitate the particles. That means that this influence of the seepage pressure always acts in the direction of flow and can change or influence the effective stress. So, that we will be seeing very shortly. So, seepage pressure is due to the flow of water through voids. That is what we have just now discussed, and because of the frictional drag, the hydraulic head decreases steadily on every flow line. So, for a particular cross section can have innumerable number of flow lines. So, through this flow line what will happen is that a gradual or a steady dissipation of the energy takes place. So, because of the frictional drag, the hydraulic head decreases steadily on every flow line. So, let us look into the concept once again. When flow of water through the, before looking into the flow of water through soils, let us look, we defined earlier that Tarjagi's concept of effective stress, sigma S, that is total stress, is equal to sigma dash plus UW, where sigma dash is the effective stress and UW is the pore water pressure. So, let us see the changes in geostatic stress with flow of water through soil. So, when water flows through the soil, it exerts the drag force called seepage forces. That is what we have just now discussed, that when water flows through the soil, it spends an energy in the form to induce a frictional drag onto the soil particles. So, it exerts drag forces called seepage forces on individual grains of the soils. So, the presence of the seepage forces which cause changes in the direction of the flow will cause the changes in the pore water pressure and effective stresses in the soil. So, when these seepage pressures act, then they finally influence the effective stresses. So, now let us consider three different cases. In the first case, like what we did before when we discussed about hydrostatic conditions when no flow is taking place, let us consider the same case again as a case 1. So, case 1, when no flow takes place to the soil, that means that hydrostatic condition. So, consider a container having water head which is H1 and above H1 is the level of the water above the top surface of the soil. So, this portion of the soil, this portion is filled with a soil of height H and it is connected to a stem and maintained that this water level is maintained. So, this is the water source here, a continuous source, and this particular head is maintained by taking this water out and assuming that this particular portion of the soil is completely saturated and the interconnected here from the stem, then this particular portion is filled with water and maintain this level, and this level is the extra water is collected outside. So, if at all flow to take place, then water flows either depending upon the location of the stem. So, here this location is maintained such a way that the level of the water in the stem is equal to the level of the water in this main container. So, let us look in that particular case, if the soil is completely saturated, then gamma sat, saturated unit weight of the soil, gamma W is the unit weight of the water. So, the total stress variation with depth can be given as at a particular point at the top surface where that water surface is there, atmospheric surface. So, pressure is equal to 0, it is gamma W, here it is 0, and at this particular point it is gamma W H1, that is the water pressure here is gamma W H1, At point B, if you call this as point B and this as point A, at this point it is gamma W H1 plus gamma sat H, because gamma sat H is the saturated unit weight of the soil and gamma W H1 is water unit weight which is acting. So, the total stress acting over the unit, suppose if this is having a unit area, then gamma W H1 plus gamma sat H. So, the pore water pressure distribution with depth for this case can be given like this. At top surface it is 0. So, here the total stress is 0, here the pore water pressure is 0 because of the atmospheric surface, and here the water pressure is gamma W H1, and at this particular point it is the ordinate here is gamma W H1 plus H. So, what it has is that because of the same water, the slope of this line is same, but here there is a water and then soil. So, there is a change in the slope of the line can be noted. So, here gamma W H1 and here at this point it is gamma W into H1 plus H. So, the effective stress is nothing but total stress minus pore water pressure. So, that is obtained here as 0 and 0 at this point, that is gamma W H1 minus gamma W H1 is said to be 0 here, and at this point when you subtract gamma W H1 plus gamma sat H minus gamma W H1 minus gamma W H is reduces to gamma sat minus gamma W into H, that is nothing but gamma dash H, that is submerged unit weight of the water soil plus submerged unit weight of the soil times H. So, this indicates that we have seen that when no flow takes place, when the particularly here there is no head loss between point 1 and 2. So, if you look into heat here, if this is taken as a datum, so total head at this point is H1 plus H, and at this point it is also H1 plus H. So, because of that what will happen is that the no head loss. So, in the process what will happen is that the delta H is equal to 0. So, no flow can take place between points A and B because of this particular condition. So, in the process like we discussed in the previous lectures, now the effective stress, that is the distribution is 0 at the top of the soil surface, and at the bottom of the soil surface it will be around gamma dash H also. That indicates that this whatever may be the height of the H1 is independent of the height of the water resting on the soil bed. So, this we already discussed. This is once again we are discussing as a case 1 for this condition. So, no flow can take place. So, because head loss delta H is equal to 0. So, no change in the effective stress. So, whatever may be the height of the H1 value here, the effective stress will remain unchanged. Now, consider a case 2 where a particular arrangement which is shown in this slide is considered. When flow takes place to the soil, but a downward flow. Why downward? Let us look into it. Let us consider now this stem has been lowered by a distance, vertical distance, or by H, the small h, and similarly here it is H1 and here it is H. So, the total stress which is in the main container is gamma W H1, and at this particular point it is gamma W H1 plus gamma sat H. So, this is nothing but H1, and the thickness of the soil specimen within the container is H. So, gamma W H1 and then here it is gamma W H1 plus gamma sat H. So, like from the previous case and this case, total stress remains unchanged. Now, the total head which is available here will be like for example, here the U will be gamma W H1, and if the no flow to take place, then what will happen is that the gamma W into H1 plus H is the water pressure. It is supposed to be, you should get at that bottom portion when the no flow to take place. In the previous case what we got is that gamma W into H1 plus H. Now, in this case, because of this position, there is head loss which is taking place between point A and point B. So, that head loss is nothing but indicated by small h, and the thickness of the soil bed here is capital H. So, the hydraulic gradient said to be small h by capital H. So, what is happening is that here it is having the head which is driving the flow is small h is there here, and then it is said to be 0 here. That means that the water will have energy of small h. So, at the 50% of the height, the 50% of the head loss will occur. At somewhere around 25% of the height from the top surface, it will be around 25% of the head loss will occur. At 3/4 of the distance from the top surface, so 75% of the energy will be lost. So, at the end of the after crossing the full thickness of the soil specimen, so the head loss is supposed to be 0, that is h is equal to 0. So, here if by eventuality of that we will be seeing in the next slide, but here because of this particular phenomena, what will happen is that the pore water pressure which is available at top of the soil sample will now get reduced to gamma W into H1 plus capital H minus small h, gamma W into capital H1 plus capital H minus small h. So, that is the reduced pore water pressure, because what happened is that much is transferred in the form of a seepage pressure to the soil grains. Now, if you look the effective stress now, at this point the ordinate here total stress is gamma W H1 and here it is gamma W H1, that means that here the effective stress is 0, at this point it is 0. So, in this zone it remains unchanged, but when you come to the bottom now, because of the change in pressure, what happens is that change in pore water pressure, that effective stress increases. Why? That let us look into here. So, that is nothing but total stress is equal to gamma W H1 plus gamma sat H minus this particular ordinate, if you consider here, minus gamma W into H1 plus H minus small h. So, if you simplify this, it reduces to gamma dash H plus H gamma W. When the no flow is taking place, we do not have this term H gamma W. Now, this H gamma W is adding. So, this is actually a component which is actually being spent in the form of a seepage pressure. So, because of this total head loss occurring available at this point and at this point, the head loss is as it is occurring from top to bottom, the flow takes place from top to bottom, that is the downward direction. So, when the flow takes place from top to bottom, that is in the direction that is in the downward direction, then what will happen is that what we are seeing is that the effective stress increases. So, downward flow increases the effective stress in soil, that is what we have seen, the downward flow increases the effective stresses in soil. That means that because of the frictional drag, these particles will be pushed to the denser positions. In the process, there will be an increase, more and more the effective stress is generated because of this decrease in the pore water pressure. The total stress remains same, but decrease in the pore water pressure occurs because of the loss of the energy in when the water tries to flow through the soil. Now, consider the same case 2 again, and let us try to understand once again the mechanics, why the flow which is taking place in the downward direction, and how at what different levels, how exactly we can determine the pore water pressure. So, the same case, what we discussed is that slightly the arrangement is shown here, which is nothing but the similar arrangement, but which is the provision has been made to show these standpipes. Let us assume that it has got the water level H1 like in the previous slide, and H is the thickness of the soil bed, and this is the top surface is the point A, and the bottom surface is the point B here, and assume here that there is a constant source of water, and this head H1 is maintained by collecting the surplus water, and it is connected to a stem which is H units below this particular upstream water level. So, in the process what will happen is that because of this the water flows in the downward direction, water flows downward. When the steady seepage conditions are established, then what will happen is that the amount of water flowing through this soil which is collected here, that is nothing but the discharge, which is the amount of water flowing through the soil. So, the amount of water collected in a given time we can estimate. So, based on that we estimate the coefficient of permeability value, which we are going to see in the next lecture about how to determine this coefficient of permeability of a given soil in the laboratory, as well as some field methods to determine this particular parameter. Now, let us consider if this particular portion is treated as a datum, that is the reference datum, then total head at point A is H plus H1, because the pressure head is H1 and elevation head A is H meters above the datum. So, the total head is equal to the pressure head is H1, elevation head is H. So, the total head at A is H plus H1. Now, when you come to the portion that is the point B, which is at the bottom of the sample, the total head at B is equal to H plus H1 minus H. This is because here the elevation head is 0, the pressure head is H plus H1 minus H, because that much head loss is already occurred. That means that here if you look into it, here H is the energy which is available, that is head which is available between this point to this point, that is the head loss which is occurring from upstream end to downstream end over a length H. So, the ratio of this slope of this line is nothing but the hydraulic gradient I. So, at this if you look into this here, at this point A, it has got the full head which is had to dissipate. At this point at a certain depth, there is a certain head component which is there. So, that is nothing but I is equal to H by H. So, H is equal to I H. So, there is a, for example, if this is Z is equal to H by 2, then we can say that 50% of the head loss is already occurred. When this Z is say H, then complete head loss occurs. So, at this particular point, so when Z is equal to say now H, small h. So, total head at B now is, because pressure head is now H plus H1 minus H, that is this level H plus H1 minus H, and elevation head is 0. Because of this total head at B is equal to H plus H1 minus H. So, if you look into it, the difference between H plus total head at A and B is nothing but small h, that is the one which is driving the water to flow in the downward direction. So, similarly, now whatever the pressure distribution what we got now can be interpreted like this. So, at this particular point, because of the atmospheric pressure, the pressure is 0, water pressure is 0. At this point A, it is gamma W H1. So, here what we said is also gamma W H1, that is H1 is the pressure head which is available at point A, and H is the elevation. Then the total head we are here we are saying is that total head is at A is equal to H plus H1. So, here at a certain point from the top surface, say from A, that is at certain point within the soil, say Z, then that ordinate can be given as H1 plus Z minus IH. So, this Z can be if it is say Z is equal to full soil depth, then it changes to gamma W into H1 plus capital H minus small I h. So, this is the I h is nothing but the is written as I is equal to H by small h. So, previously what we are writing is that H1 plus capital H1 plus capital H minus small h. The small h is now written in terms of hydraulic gradient times thickness of the soil specimen. So, the effective, suppose if the no flow takes place, what we have this ordinate is now what we are seeing is gamma W into H1 plus H. So, because of this flow which is taking place, this much particular portion of the pore water pressure is lost from point A to point B. So, that is transferred to the soil grains in the form as an effective stress. So, that actually results as an effective stress. So, similar mechanism can be explained for when the flow is taking place in the upward direction. So, let us look into it as a case 3. So, when the flow takes place through soil in the upward direction, that means that assume that now the similar arrangement, but what we did is that this stem has been taken H meters or H units above this level. So, this serves as a upstream surface and this serves as the downstream surface. So, water flow, when I am actually having a continuous source of water, when this head is maintained here in the stem which is provided here, and when extra water which is collected here, this is nothing but the one when the steady state seepage conditions are established, then the amount of water flowing to the soil can be, if it is collected here, that is actually resulting as a can be measured again as a discharge and then to reduce permeability. But in this case, because of this difference in head between this point and head at this point is more than head at this point, in view of that, what will happen is that the flow takes place in the upward direction. So, what will happen to this geostatic stresses when the flow takes place in upward direction? That let us look into this like this. So, if you look into the total stress distribution with the depth, it remains same because same height h1 and h. So, which reduced to gamma w h1 and gamma w h1 plus gamma sat h, which remains same like in the previous case, which is also same when the flow is not taking place. But the only the difference will come is that when the flow which taking place, and also depends upon the direction of the flow. So, here in this case the pore water pressure is obtained like this. This is at this point it is 0 and at this point it is gamma w h1 which is same as this, and when here when the flow is not taking place, we have actually said that gamma w into h1 plus h is the pore water pressure. But here because of this difference in head, the flow takes place in this vertical direction. So, in the process what will happen is that now the head that is which is driving the flow, the total head is nothing but, if this is taken as a datum, h plus h1 plus small h, that is which is nothing but gamma w into h1 plus capital H plus small h. So, the total head at this point is which is h1 plus capital H1 plus capital H plus small h, and here because the dissipation of the energy occurs, because of that what will happen is that the head there will be at this particular point it will be H1. So, if you look into it here, gamma w into H1 plus capital H1 plus capital H plus small h. So, that is now the pore water pressure is increasing in this particular case. Now, let us look what will happen when this is subtracted from the existing total stress here. So, at this point the pressure is 0. So, in this zone there is no change again like in the previous case, but here what exactly is happening is that if you look into it here, the total stress is decreasing because there is an increase in the pore water pressure. So, at this particular point the pressure is now gamma dash h minus h gamma w. So, in the previous case we got like gamma dash h plus h gamma w when the water flows in the downward direction. So, in the upward direction now what is happening is that the effective stress decreases. So, when this particular head is say increase, then at one certain point what will happen is that the effective stress can even reduce to 0. If further if it is increased, then what will happen is that the effective stress reduced to a negative value. That means that all particles are agitated and there is no interaction between particles, which represents something like most fluid situation or a boiling situation. So, gamma dash h minus I h gamma w, where I is equal to h by h, that is small h by capital H. So, by writing h is equal to I times capital H, then we can write this effective stress at this particular point is gamma dash h minus h gamma w. So, upward flow decreases the effective stress in soil. So, in the previous case when the flow is downward, there is an increase in effective stress. When the no flow is taking place, no change in the effective stress. When the flow is taking place in the downward direction, then there is an increase in effective stress. When the flow is taking place in upward direction, then there is a reduction in the effective stress. So, this particular upward flow conditions which can occur because of the some natural existing features can create failures for the geotechnical structures. Now, let us look once again into the explanation for the case 3. Here the same situation is explained here, where you will see that the H is the capital H is the thickness of the soil specimen, and H1 is the head of the water which is resting here. So, the extra water which is collected here is the, after establishing the steady seepage conditions, that is the one which is actually when flow is taking place in the upward direction, that is the direction of the flow is this. So, the head loss between these 2 points is the small h, the length of the soil specimen which is subjected to flow is capital H. So, the hydraulic gradient is head h which is available here, which is driving the flow, is small h, which is here and 0 at this particular point. The slope of this line is nothing but the hydraulic gradient is I is equal to small h by capital H. Now, if you put at different points, say at this point and at this point and at this point, and if this point is called as A and if this point is termed as B, which is shown here, then if this particular plane is taken as datum, then elevation head is 0. The pressure head, if the water is tapped here, then it will rise to a head which is equivalent to H plus H1 plus small h. That means that the head which is there is this much. That means here what will happen is at this particular point elevation head is 0. So, the total head at point A is equal to H plus, that is capital H plus small h plus capital H1. When you come to this particular point B, already this h is now reduced to 0. So, the head which is available is now is pressure head is H1 plus H. So, the total head which is now equivalent to H1 plus H. Okay. So, in the process we can say that the head loss which is occurring between these 2 points, which is the difference between the total head at point A to the total head at point B, is nothing but H1 plus capital H plus small h minus H1 plus h gives rise to that h which is taking place over a length h. So, like this what is happening is that there is a pore water pressure which is there, and by the time it comes out which decreases. So, in the process that means that there is an increase in pore water pressure here, that means that at this particular point where this head is maintained, there is a decrease in the effective stress. At this point again it remains unchanged. So, having seen the effect of seepage or a flow of water through this effective stresses, that is effect of seepage on effective stresses. So, seepage is the flow of water through soil, that is what we have discussed. It exerts a frictional drag on the soil particles and in the form of a force called seepage forces, and which results in head loss. Because of the mobilization of the seepage forces, it results in that head loss which is actually driving the flow. And seepage flows play a very important role in destabilizing geotechnical structures. Like we discussed just now, this particularly the seepage flows play very important role in destabilizing certain geotechnical structures, which we are going to see very shortly. So, here to summarize, the downward seepage increases the effective stress. So, when the flow is taking place, what we discussed is that there is an increase in the effective stress, which is nothing but sigma dash is equal to gamma dash h plus Ps times capital H. So, this Ps is nothing but I gamma w, which now we have written gamma dash h plus I gamma w h. This I gamma w which is nothing but seepage force per unit volume, and which has got the unit weights, which has got the units as that of unit weight, like kilonewton per meter cube in SI units.